All right, let's review what. So today I wanted to talk about. Let's see. Yeah, main theorems, the locality theorem and which can also be seen as a geometric cobordism hypothesis part 1, and the actual GCH part 2, which tells us how to classify and compute functorial field series. So let me first start by reviewing what we did so far. We defined, starting from any dimension D, f is 0, we define a site, the site of families of D-dimensional manifolds and their open embeddings, or more precisely, families of open embeddings. So objects are submersions T over U with D-dimensional fibers. Morphisms are commutative squares, where the chop map is an open embedding on every fiber. So for every point of U1, the induced map between fibers from the fiber over this point to the fiber over its image in U. Oops, why is this U true? And covering families are induced by the forgetful functor that discards the map to U and keeps only the total space. So a family of maps is a covering family if so generating covering families are precisely those families of maps where both maps are open embeddings, and the chop maps cover the codomain. And we also discussed how this site can be enriched over the site of smooth sets. So these are sheaves of sets on the Cartesian spaces site. So you really just have to say what it means to specify a smooth family of such morphisms. Then we have an obvious way to do it. And then finally, we define the model category of geometric structures of dimension D, as the category of enriched pre-sheaves on this site with values in smooth simplicial sets. So these are sheaves of simplicial sets on the site of Cartesian spaces, so like this one, but with simplicial sets. And we equip such functors with the Czech local model structure. Strictly speaking, I would have to specify for you whether it is the injective or projective. Typically, we find injective easier to use because all objects are cofibrant. Cofibrant means you don't have to cofibrantly replace them. And previously, we also discussed how to construct the model's category of smooth, symmetric monoidal infinity D categories. These turned out to be pre-sheaves on the product of categories of Cartesian spaces, gamma spaces, and D copies of the category delta. Just insert something here. And strictly speaking, if in the enriched case we will need smooth simplicial sets as values. But in case you find this confusing, you can ignore smooth simplicial sets because the model structure in smooth simplicial sets is equivalent to the usual Kang-Quillen model structure in simplicial sets. So this is only added for our convenience and not truly necessary. Okay, and we discuss how introduce a model structure which will encode the Chev descent in the Cartesian direction, the Siegel condition in the gamma direction, the complete Siegel space conditions in each of the d delta directions, and the globularity condition for the whole product of delta, d copies of delta. All right. So I think at this point we can actually formulate the first theorem. So recall that we previously formulated the Bordism, the d-dimensional Bordism category with geometric structures. And we had both the enriched and unenriched versions. So in principle, the theorem is true for both. Let me just make it enriched so that it matches what we need for the GCH part 2, because part 2 requires enrichments. But in any case, we define a functor which sends a geometric structure to the corresponding category of Bordisms, which is a smooth symmetric monoidal infinity D category. And the assertion of the theorem is that this functor is a left Quillen functor. In more conventional terms, we can say Bord D preserves homotopy co-limits. So it's a homotopy co-continuous functor. And this has immediate consequences. So first of all, let me point out that homotopy co-continuous functors from categories of sheaves, like this category of geometric structures, these are also known as infinity co-sheaves. So Bord D is an infinity co-sheaf. And it has a Reich adjoint functor. The Reich adjoint functor we ended up denoting in the paper by just a subscript D. And you can easily see what it is. The Reich adjoint will send a smooth symmetric monoidal infinity D category to a geometric structure. And what is the geometric structure? Well, if you use the traditional trick with adjunctions, how to compute the Reich adjoint functor, well, if you take some V, an object in here, a smooth symmetric monoidal infinity D category, apply the Reich adjoint functor to get a geometric structure, which we call VD, and evaluate it on some object on this of the side frame D, then by the adjunction property, this will be simply the simplicial set of maps from the d-dimensional Bordism category with a very special geometric structure given by this representable object with values in the category V. So this is quite literally the simplicial set of certain functorial field theories. namely with this very special geometric structure. And just to see how special this geometric structure is, imagine for a second that U is a point, which is the most representative case. Then the boardisms in this category, boardisms will be equipped with an embedding into a d-dimensional manifold T. So you have d-dimensional boardisms, and they are equipped into a d-dimensional manifold. So the typical case would be if T over U is Rd over a point, in which case your boardisms are simply embedded into Rd. In other words, the ambient manifold of a boardism is just an open subset of Rd. So this kind of is a very restrictive condition on boardisms. And yet you do have interesting non-trivial functorial field series. And what's more, as we will see in a second, knowing functorial field series of this very restrictive type tells you everything you need to know about functorial field series in general. So let's recall how to compute the space of functorial field series in general. We previously defined it as a derived simplicial set of maps from the d-dimensional boardism category with some geometric structure S with values in some smooth symmetric monoidal infinity D category, capital V. This derived mapping simplicial set is difficult to compute.
Excuse me, Dmitri.
Yep.
You mean?
Yeah.
Instead of writing S set in this assignment VD, don't you want to write map or something like this?
Yeah. I mean, I wanted to remind you that map means, of course, this is a simplicial set of maps because, I mean, in principle, you can have, and I guess if you really want to be very pedantic, you can also say a smooth simplicial set, but again, as I mentioned, these are equivalent, so it's only a matter of convenience. If you don't want to use smooth simplicial sets, you would have to take a singular simplicial set in many places, and that's the only difference. Yeah, so that's in principle, map perhaps is a more common notation, but in principle, SSEC is also used, I guess. Okay, so now by the adjunction, more precisely derived adjunction, you can move a left adjoint. So notice board D, since all objects in geometric structures are cofibrant, board D is its own derived functor. There is no need to derive board D. And so you can move it to the right side of this mapping object just by removing board D from the left side and putting this adjoint on the right side, assuming capital V is fibrant. If it is not, you will have to fibrantly replace it. But notice, even though the fibrant replacement can be very difficult, it's not necessary to go in practice because, again, this is a theoretical computation, and there are other ways to compute these spaces and what I just mentioned. And so what is the takeaway from here? The takeaway is that this is a mapping, this last object is a mapping simplicial set or smooth simplicial set in a much simpler category. In the category of geometric structures. These are just certain sheaves on a certain site. And as you can already guess, it's much easier to compute in sheaves on a certain site than to compute with smooth symmetric monoidal infinity D categories. But of course, if you look at this formula, you are wondering how to compute this VD, this right adjoint. Because if you look at the definition or description of the right adjoint here, if you look at the right side, you will see that the right side is basically the space of functorial field series with a certain geometric structure. So it would seem that VD is just as difficult to compute as the original mapping simplicial set here. But as it turns out, the second part of the GCH takes care of exactly this problem. It allows you to compute VD much more efficiently. But before we move on, let me first ask if there are any questions about this statement.
So maybe if I remember correctly, you could also equally well replace femd by femd-cart-d, right?
Correct, yes. And in fact, this will be mentioned 2 pages below. Yeah,
Okay.
we will talk briefly about this, yes. I will implicitly make use of it on the next page, in fact, yeah.
As I understand, we need to do this, yes, rewriting for simplifying computations, as I understand, yes, the last row.
Yeah, I'm not going to say simplifying as much as enabling them. I don't think it's anybody could do a direct computation here at all. So it's really, this is, I mean, difficult really means probably, difficult in this case means nobody can compute it as of today directly. So of course, this can actually be computed in many cases. Yeah. So in particular, by constructing a map from S to VD, we can construct a functorial field theory, which is probably the most interesting part in this computation. But also notice it is also possible to compute the whole space of functorial field series here as a mapping simplicial set here. And that's important for the Stolz-Geithner program.
What are the main obstacles for computing previous equation about from category of Bardism to any symmetric monoidal category?
What are the main obstacles to computing what? Sorry?
The previous equation. We distend the previous equation to this equation, and I'm trying to understand what are the obstacles in computations when we have category of Bardism and V category.
Well, here it will be very difficult to compute anything because
yes,
there are
there which obstacles we can.
Well, just look at the definitions. We would have to compute inside this category. And you can see already by the description, it's really complicated. And so even just writing down a point in the space would be very difficult, let alone computing anything about it. It's just, there's a lot of stuff to manipulate and keep track of. And it is feasible maybe to do it once in a theoretical paper, like ours, but not for computing anything practical in practice. Okay, more questions? Probably I should, at some point I will explain the geometric intuition for the infinity co-sheaf condition, but maybe for now let me just state the part 2. So part 2 has the same context as the previous theorem. We still have a fixed dimension D. We have a fixed smooth symmetric monoidal infinity D category, capital V. And now we are interested in computing the right side of the mapping simplicial object, the VD construction. Recall that VD, by definition, essentially is Functorial field series with a very special geometric structure, the representable geometric structure, and maybe at this point we should split. Hope it's not too small. All right. And we are only going to compute not on arbitrary objects in the set, which, as you may recall, are arbitrary submersions, but we'll compute it on submersions of a very special type, which are just projections from Rd times U to U. You may ask, well, why is it sufficient to compute on such guys? And the answer is, any object here, imagine if U is just a point, which is the representative case. U is just a point, then T is a d-dimensional manifold, and a d-dimensional manifold has a good open cover by Rd, by manifolds diffeomorphic to Rd. And this allows you to reconstruct, since Vd is a sheaf, this allows you to reconstruct the value of Vd on any object from its values on objects of this form, which are just projection maps. And that's why we are only going to talk about these simple objects. So that's eventually will be called cart D, where cart stands for Cartesian. It's this fiber that is Cartesian. And the crucial observation here is that we have an evaluation map. So this VD, I should probably have said a bit more about the evaluation map. Maybe I shouldn't. Okay, this is so weird. So let me say a few words about this evaluation map. So let's recall that this here is the simplicial set or smooth simplicial set of maps from the d-dimensional Bordism category or enriched Bordism category with geometric structure given by fiberwise open embeddings into RD. And the category of values is capital V. Now let's recall what a Bordism category is. Let's say I think I wrote somewhere here. Okay, yeah. So so this is a mapping simplicial set, and here again I will assume V to be fibrant. This is a mapping simplicial set in this category, in the category of pre-sheaves of this form. And what we can do is, so a point here in the space is a natural transformation of two such pre-sheaves, and the natural transformation can be evaluated at any object in this category. So what I'm going to do, I'm going to evaluate it on objects of the form U, a Cartesian space, 1 as an object in gamma, and a bunch of zeros repeated d times as an object in delta d. And I'm going to land, a priori, I'm going to land inside the value of V evaluated at the same object. So it will be a map. So the component of the natural transformation indexed by this object a priori is just a map of simplicial sets or smooth simplicial sets between the corresponding values at the indicated object. So let me maybe spell it more carefully. So this will be a mapping. We are going to land inside a mapping simplicial set where you would have, well, basically both of those would be evaluated at this object. And I'm sorry, it's going to be a bit of a mess. You know what? Let me actually create a new page, because this is too important to be glossed over. And I'm going to do magic called cut and paste. It's always a problem not to. Okay. And now cut. And how do I do paste? Excellent. Yeah. So simply evaluating a natural transformation at this object will produce a map to the corresponding objects evaluated at this object. So it's going to look a bit messy, but it's very simple. Comma, and then the same for capital V. So what's the meaning of evaluation, of such an evaluation? The idea is that d copies of 0 encode precisely objects in an infinity D category. Likewise, evaluating on the object 1 in gamma extracts the underlying object of a commutative monoid. In our case, it will extract, so evaluation at this one will extract the underlying infinity D category, from which you then extract its objects. And then evaluation at U extracts the simplicial set of U indexed families of such objects. So what we are doing here, this evaluation, it extracts U indexed families of objects. So we are looking at what our functorial field theory does to U-indexed families of objects. Okay, any questions so far?
Maybe why is it enough to extract objects via 0D of infinity 1 category instead of infinity n category? So why can we evaluate it bracket 1 bracket instead of bracket, I guess, L or N bracket?
You mean this bracket or this bracket?
The first one.
So this one is a gamma. So the meaning of this, let's recall that generally speaking, if you evaluate at some m in gamma, so depending on which model you prefer for gamma, this will either correspond to a finite set with m elements or a finite pointed set with m elements together with a base point. And the meaning of such evaluation is that evaluating on such an object gives you m tuples of multipliable elements. So in our case, evaluation of m in gamma will give you m tuples of Bordisms for which we can take disjoint unions of Bordisms in the tuple. But here, I'm not planning to take any disjoint unions. I just want to look at a single object. I want to look at a single object which looks like a zero Bordism, which is a point. So since I'm not planning to take any unions, I only need a one tuple. I need a single element, a single Bordism. So evaluation of 1 corresponds to just Bordisms. Or a one tuple is just a single Bordism, so a single Bordism. Not a couple of Bordisms, but a single Bordism. So that's the meaning of evaluation of 1 in gamma.
I see. Thank you.
Yeah. All right. And 0D is precisely responsible for objects, and U is responsible for U-indexed families. All right, so now I'm going to write down a I mean, we are basically almost done. Maybe I should have been more specific about the meaning of these symbols here. So FD refers to fully dualizable. And that's what we discussed all the previous lecture. And we have seen how any functorial field theory flows inside fully dualizable objects. What's the meaning of the cross? The meaning of the cross is that you want to discard non-invertible K-morphisms, where K is between 0 and D. And how can this be accomplished in practice in the language of complete Siegel spaces or complete n-fold Siegel spaces? How can this be accomplished? Well, this is simply given by if you have a smooth symmetric monoidal infinity D category where all objects and morphisms are fully dualizable, then discarding non-invertible, or more generally, any smooth symmetric monoidal infinity D category, non-invertible K-morphisms are going to be encoded by higher simplices. So I guess if you take more than 0 here, this will be responsible for encoding non-invertible morphisms. Whereas, as we have seen before, thanks to the completeness condition enforces the following reality that evaluating at the 0 simplex will extract precisely the invertible morphisms. So if you want to discard non-invertible morphisms, that amounts to precisely extracting the invertible K-morphisms for OK. And I should have probably said at most. Yes. So this simply amounts to evaluating the object, which is a bunch of zeros inside delta D. And that's exactly what we are doing here. So basically, we already landed inside the correct object, right? We landed inside the object of the infinity groupoid. So this object here really encodes the, if you want, the infinity groupoid of U-indexed families of objects and invertible K-morphisms where K is greater than 0. And notice, of course, if K is greater than D, then D plus 1 morphisms and higher are invertible by our construction. But if K is at most D, then we are just taking the invertible ones. And that's precisely, so this precisely requires V to be fibrant. Because fibrancy in particular includes the completeness condition. So to be fibrant, more precisely complete. And it is a completeness condition that guarantees that the evaluation at 0 will be precisely the invertible morphisms, the infinity groupoid of objects and invertible morphisms. So with the exception of full dualizability, which we know we are going to, so any functorial field theory is going to land inside fully dualizable objects always, so that's a tautological addition. Basically, this object is precisely the right side here. So I can also write that this is the same as the fully dualizable part evaluated on U1 and 0D. And as I said before, we factor through the fully dualizable part automatically. So we are almost there. We almost constructed the map we want. This evaluation almost gets us where we need to be, with the exception that here we have this simplicial set. And what we really want to land in is just this object here. So as a second step, I'm going to pick some point here, some point in this evaluation of the Bordism category, and evaluate at this point, which will land me inside this object. Oh, sorry. Which will land me inside this object. So here, this arrow is going to evaluate like a certain point inside the simplicial set, which I'm going to construct now. And you are going to land inside here. So what is the point? It's so evaluate on what? Evaluate on, let me call it 0. You will see why. So we evaluate these maps, these evaluate at the point 0. Yeah, let's call it 0. So what exactly is 0? 0, it's a bold 0. Is a point in the simplicial set. This point encodes a U-indexed family of objects with given by zero-dimensional Bordisms that are embedded into RD. And let's recall how such a Bordism looks like. So what does a zero-dimensional Bordism look like? It's a zero Bordism, first of all, has an ambient manifold, which in our case is just going to be RD. And the other data that we have to specify is a U-indexed, so C is going to be a U-indexed family of cut grids. And strictly speaking, there is also P, which in our case is going to be completely trivial because P is going to be a map from M to 1. And basically, it will send everything to so everything will be sent. So all of M maps to the only point here, the only point which is not the base point. This is just an expression of the tautological fact that we are interested in a single Bordism here. So really what I have to specify is a U-indexed family of cut grids. That's very easy to do because this amounts to specifying for every point in U, specifying a cut grid for the corresponding point, corresponding fiber here. And all fibers are the same, they are all RD. So really I just have to specify a U-index family of cut grids in RD. And it's the simplest possible family you can imagine. So I have D directions, and in each direction I simply take the corresponding coordinate plane. So in dimension 2, for example, you will see just the x-axis and the y-axis. And let's suppose that each cut is equipped with a normal orientation, and the orientation is going to always be going in the increasing direction of coordinates. So this part is greater than 0, this part is less than 0, and likewise here. So morally, this is just encoding a single point as a zero Bordism. But remember, all Bordisms are equipped with a d-dimensional germ or a d-dimensional color, and this color will be some arbitrarily small neighborhood of this point here. So that's what you really should think of, is you are encoding a point with a d-dimensional neighborhood, and specifically they are encoding the point 0 in RD with its canonical cuts and a d-dimensional neighborhood. So that's literally the simplest possible type of a zero Bordism. Just a point. And this completes the definition of the evaluation map. Actually, write down. Any questions about the evaluation map? Okay, so the part 2 of GCH, the actual GCH, says the evaluation map is a weak equivalence. Maybe I should highlight it in red. So the red part is the actual theorem. It says this evaluation map is a weak equivalence. In other words, the value of this VD at some object of this form is precisely the infinity groupoid of fully generalizable objects, U families of fully generalizable objects, and there are isomorphisms in all K morphisms are isomorphisms for all K. That's what VD is. Okay, any questions about the statement of the second theorem?
Dmitri, one question. I hope you can hear
Yeah,
me. So when we look at Lurie's paper, and when we say we don't have smoothness involved, but U is like R0, does the smooth version follow from Lurie's result if we assume Lurie is...
Sorry, could you repeat? You are breaking up. Your connection is kind of choppy. Alex, are you still there? Alex, you're muted.
Yes, but I might have problems with my connection.
Okay, we can hear you now.
Okay, so my question was whether or not the Lurie's statement of the cobordism hypothesis, if this one already implies, so if you assume this is true, if this implies the smooth case.
Imply the smooth case.
Like the smooth geometric, the smooth framed geometric cobordism hypothesis. Like.
Why would it imply? Sorry, because I mean I can see why the smooth case implies Lurie's case, because Lurie's notion of a topological structure is a special case of a geometric structure. So how do you want to go in the opposite direction?
So I mean the framed geometric cobordism hypothesis is really a smooth version of like the ordinary topological cobordism hypothesis, right?
Yes.
So you just smoothly vary everything. But so the question would be, if you know it at a point like at R0, could you just collect the families together, like for every value, sort of for every parametrized element in your U family? Could you just collect them together and make it into, and say that maybe you could deduce it from this already? So this would be my question.
Yeah, that's a good question. I mean, I can see what you're trying to say. Like it's like if we just restrict our attention to a single U, it's like perhaps we can just say the target category should be taken to be just U families of objects in the original category, and that's just an ordinary yeah, there are let's see if yeah, you have to like look very careful at the, like, in order for this to make sense, like it doesn't follow formally. I mean, and it's unclear if it can be modified to be, because this U here on the left side, it enters in the construction of the bordism category. Its smooth structure participates directly in the definition of the bordism category. If you recall how we, well, it's probably buried somewhere. Let's see if I can find anything that could be relevant. Yeah, I mean, it's buried in this definition, basically. Or maybe I should scroll up further to, yeah, when we evaluate this geometric structure, we capture the smooth structure of U. And this smooth structure of U also controls how cuts can move around. So in order to somehow deduce our escapement from Lurie escapement, for example, you would have at the very least to connect or somehow obtain our bordism category, smooth bordism category, or more precisely, you would have to show that U families, smooth U families of bordisms can be reduced to a single bordism in Lurie's bordism category. And to be honest, it's far from obvious to me that this can be done. Because in our smooth bordism category, cuts can move around, they can merge. And in Lurie's case, it's specifically adapted to the topological bordism category. So it's unclear if it could be done, and if it could be done, maybe it would be a separate. You would have to prove it separately to some extent, and it's to be honest, like Lurie's escapement is nowhere nearly precise enough to be connected to ours, I guess. So that's the problem. So ultimately, we don't really know some of the details in his definition. So it's, but I mean, I would agree that on a very rough level, I mean, you would say, oh yeah, the usual cobordism hypothesis would, in particular, apply to the category where objects are smooth U-indexed families of objects in a smooth symmetric monoidal infinity D category. And this somehow perhaps should imply the escapement. So it looks at least formally similar, yes. So it's a perhaps one could try to say more, but as I said, it's to me it's far from obvious if it can be done.
Thank you.
Yeah. Any more questions? Okay, so let me. So this statement only explains how to compute VD, how to compute its individual value, and only up to a weak equivalence. You may notice that in the statement we need here, VD is an object of the same type as S. It's a geometric structure, meaning it is a pre-sheaf on the side from D. So there is more to a pre-sheaf than just its individual values considered up to a weak equivalence. So, however, even though the statement itself only talks about individual values, it can be easily leveraged to produce a practical recipe to compute VD, or rather some pre-sheaf weakly equivalent to VD as a pre-sheaf. So not just its individual values, but the whole pre-sheaf as a geometric structure. And the way this works in typical complications would be as follows. First, you would guess some, so you already know what, so what we want to do is here is we want to compute something, some W weakly equivalent to VD. And you already know that individual values of W are weakly equivalent to this space here, which you can easily compute and easily write down. So what you do is you guess some W based on this knowledge, meaning specifically you guess what the structure maps of this pre-sheaf should be, And in practical situations, that's not very difficult. And we'll see probably some examples later. And you also guess a map from W to VD. And this is the only place in this recipe, or in general recipes I mentioned to you so far, where you have to do something about field series. And notice, however, it's much easier than here. You don't have to classify or compute the space of functorial field series. You only want to write down a map. And furthermore, these are functorial field series of a very special type. Their geometric structure is this representable geometric structure. And as we've seen before, in practice, this amounts to saying that bordisms are embedded into RD. So writing down such a map is much easier than you may think. It simply amounts to, in practice would typically amount to integrating some differential forms. And we'll see a specific examples a bit later. And finally, once you wrote down this map, what you do now is you look at the composition. So you evaluate any object. And you then this map is the evaluation map at points like we discussed which we discussed here. This is just the evaluation map. And what you have to show now is that this composition, which goes from W evaluated at this object to the infinity groupoid of fully generalizable objects, you have to show that this map is a weak equivalence. And notice that talking about this map makes no mention of functorial field series. So this map does not talk about functorial field series. The functorial field series were present in this corner here, but the moment I apply the evaluation map and looked at this whole composition no longer makes any use of functorial field series. And this is what makes step 3 so easy to show in practice. So step 3 is easy. So this step is easy in practice because it doesn't talk about any functorial field series. So there is a tiny bit of guesswork required in parts 1 and 2. However, it's not extremely creative because the theorem, the statement star that this map is a weak equivalence, already tells you what the values of W are weakly equivalent to. So the only guesses you have to make is how to define the structure maps. Giving a morphism in FMD, what is the associated map of values of W? So only the structure maps should be guessed, and typically this is also quite comes in quite naturally. And we will see some specific examples a bit later. So this is a very practical recipe. And what it allows you to do, it computes VD for you. So if you look at what we try to do initially, we try to compute the space of functorial field series. So maps from Bordism category, from a Bordism category to V. We use the junction to reduce it to computing a mapping simplicial set of geometric structures from S to VD. And this recipe computes VD or something weakly equivalent to it. So it allows you to say that this simplicial set of maps from S to VD can be replaced with a simplicial set of maps from S to W. Where W presumably is something very easy, relatively easier that you already wrote down. And let's see. There are further sort of recipes to how make this computation of maps from S to W. And this is what I wanted to discuss next. But first, let me ask if there are any questions left about theorem 1, theorem 2, or these recipes that we just discussed here and here. Yeah, so here is theorem 1 and theorem 2. Any questions so far?
Please may you comment a bit more again about third arrow below?
This arrow?
Well, yes. Which doesn't talk about functorial field series.
Well, this arrow is a composition of this arrow and this arrow. So this triangle is commutative. So its intuitive meaning is just a composition of these two arrows. We already know what this arrow does. It evaluates on objects. And what this arrow does, it constructs some very, very simple functorial field series where Bordisms are embedded into RD. And it does it by integrating a differential form, for example. Well, it doesn't have to be this way, but it is in many examples of practical relevance to physics. And just to give you a really, really stupid example, perhaps very roughly speaking, as a sort of little digression, you could take W maybe could be something like to be fiber-wise differential forms, say differential 1 or D forms, fiber-wise. And for example, V could be maybe, I don't know, D-fold D-looping of U1. U1 is a group of complex numbers of absolute value 1. And BD, let's recall, is a D-fold D-looping. We already talked how to define D-loopings, but if you recall, this works by Well, I'm happy to remind you how D loopings are defined, but intuitively speaking, this is a symmetric monoidal infinity D category where you only have D-morphisms. So you have a single object, a single one morphism, a single K morphism for all K less than D, and the smooth set of D-morphisms is just U1. So this type of category is a canonical target for action functionals in quantum field theory. So the expression like exponent I over H bar S of some field phi belongs to U1, right? And this whole expression is what one can call the pre-quantum action functional. The S itself is the usual action functional. And notice this expression, strictly speaking, is not correct as it is written because often you have the so-called topological term, so the topological sector, which cannot be expressed in this simple analytic form. And this is where differential geometry comes in. So in general speaking, this will be not the simple exponential, but rather the holonomy of some bundle germ. For example, in the Chern-Simons theory, this expression would be the holonomy of the Chern-Simons bundle 2 germ. And this is not just the exponent of some number, but although it could be presented as some after we make some non-canonical choices. And then we will have to show independence from such choices. But in our case, so let me just maybe give you a completely precise answer. So omega at most D. So fiber-wise differential forms of degree at most D. And then this map here essentially is quite literally an integration map. So let's call it iota. So the map from W to V. For example, let's look at what it does to dimorphisms. So you start with some differential D form. Say omega is a differential D form, fiber-wise. And then to map omega to the right side, so this VD will be a functorial, so by definition will be a functorial field theory with this representable geometric structure. So bordisms are embedded into RD. And the target category V is the default de-looping of U1. So what you do here is to write down such a simple functorial field theory, you simply say, okay, a d-dimensional bordism embedded into RD, say I have some bordism B is embedded into RD, and RD is equipped with a fiber-wise differential form omega. So what I do is I send B to the exponent of the integral of omega over B. So that's basically a very simple version of a holonomy of a bundle gerp, except there are no bundle gerps here. It's all trivial, and you're literally just integrating differential forms. So basically the takeaway here is that if you integrate a differential form over a Bordism and then take its exponent, so you land inside U1, the resulting construction is compatible with gluing, because if you glue two such Bordisms, B1 and B2, then the integral of omega over their gluing will be the sum of integrals. And when you take the exponent of a sum, you get the product of exponents. And product is precisely the composition of dimorphisms here. So that's probably the simplest possible non-topological example of a non-topological functorial field theory where you integrate a differential form. Okay, any more questions? Okay, so let me address the question of how to compute the simplicial set of maps from S to W. Like this, how to compute mapping spaces of geometric structures, which recall are just pre-sheaves on the side FMD. And here is maybe an extract from our paper, forthcoming paper on geometric structures. Although currently you can still find most of this material in the second paper. Although maybe it's a bit condensed there. So here's a legal preposition. Let me recall, first of all, previously we defined two versions of the side FMD. One was unenriched, and the other one was enriched over smooth sets. So here bold F means enriched. So these two categories we've seen before, these are unenriched geometric structures, and these are enriched geometric structures. And you have a forgetful functor from enriched geometric structures to unenriched. This functor simply restricts, so on objects, it's simply giving an enriched geometric structure, it produces an unenriched structure simply by discarding the data of enrichment. So you have the same basic pre-sheaf with the same values, but the structure maps will be now just ordinary structure maps in the usual categorical sense without any enrichment. And you have very similar versions of these sites where I put a little cart here. Cart simply means here on top we are looking at arbitrary families of manifolds. At the bottom line we are looking at families whose typical fiber is RD. And a fiber-wise version of the usual argument that says every manifold can be covered by a good open cover proves that the canonical restriction maps here and here are Quillen equivalences, which I indicated by reg tilde here. So that's one part of the proposition. Let me emphasize that the restriction maps, horizontal restriction maps, are not Quillen equivalences. There are, I guess, fewer enriched geometric structures, and there are non-enriched ones. So the horizontal maps are not equivalences, and that's fine. It's not a problem. And let me also compare something much closer to the setting of Lurie and Hopkins, which is pre-sheaves on the Cartesian side, card, valued in simplicial sets equipped with an action of the orthogonal group OD. And when I say orthogonal group, I really mean it as a simplicial group or as an infinity group. What I mean here is that it's not just a discrete group, but for example, you can take the OD as a Lie group and take a smooth singular set, or otherwise you have to account for its topology. So that's what I mean by an infinity group. And pick your favorite model. For example, the smooth singular simplicial set of OD will be a simplicial group. And we do know what it means to have an action of a simplicial group on a simplicial set. And there is a restriction map from enriched geometric structures to such pre-sheaves is defined as a composition of the restriction map to the Cartesian version. And the restriction map are upper scalar, which is induced. So this map, this diagonal map, is induced by as follows. For every Cartesian space U, we have an inclusion of the orthogonal group OD into the monoid, and here I really mean enriched monoid, of endomorphisms of this object here. And how does the inclusion work? Well, some element in this orthogonal group, let's say G. So if they have some G, an orthogonal map from RD to itself, I can map it to a morphism from RD times U over U to RD times U over U, which is simply the obvious morphism given by identity on the base space. And here I take a G times identity. So I act on every fiber in the same way. And U basically appears formally here. U is just a Cartesian space. It's all these monoids of endomorphisms for all possible choices of U are in fact homotopy equivalent to each other. That's because we have this enrichment, which basically allows you to contract U to a point. And there's a non-trivial result, which I should not call the Kisker-Maser theorem, but rather it's the smooth analog. So the Kisker-Maser theorem is the same statement, but instead of OD, instead of smooth maps, you have smooth manifolds, you have topological manifolds by the smooth analog of the Kisker-Mazur theorem. This is a bit maybe not entirely obvious, because here in this monoid, you may think you have non-invertible elements. For example, imagine embedding RD into itself, but the embedding is not a bijection, right? Say it's not surjective. So you may ask, well, how is it possible that such an element is invertible? And the answer is, this is where the enrichment becomes very important. So the inverse would be given by some map going in the opposite direction. And the composition of these two maps will not be equal to the identity, but it will be homotropic to the identity. And the crucial observation here is that an embedding which is not a bijection can be homotropic to the identity embedding, which is a bijection. So being a bijection is not a property invariant under homotopy. And that's why it turns out that all elements in this monoid happen to be invertible. And in fact, this inclusion is a weak equivalence. Okay. So, and this sort of is what is responsible for this map, and this map being a clone equivalence. So what happens is that here, a sheaf on this side, well, this side, first of all, notice it has a, for every U, it has a single object, this one. And I can restrict along this map, and I will land precisely in simplicial sets with an action of this group here. And so this is just a topological restriction map. And the fact that this is a weak equivalence of monoids shows basically that this restriction is also a clone equivalence. So geometric structures, enriched geometric structures, are clone equivalent to sheaves of simplicial sets with an action of the group OD on the Cartesian side. And the point here is that sometimes it can be easier to compute in this model here, than in this model here. And a typical computation would proceed as follows. We want to compute some simplicial set of maps from a geometric structure, which can be enriched or unenriched to W. Well, first of all, if the geometric structure is unenriched, as is the case with many of the examples we are interested in, they are just unenriched geometric structures, then you will convert it to an enriched geometric structure using the left adjoint. This functor is basically given by the left Conic extension along the embedding of FemD unenriched into FemD enriched. So it's a unique continuous functor that sends representables here because there are direct analogs here. So that's what this part does. And then, in any case, once you arrive in the enriched setting here, you apply this clone equivalence, which is just a composition of R star and Q star, to Lang in this category here. And once Lang inside this category here, it may be easier to compute here than in general. Let me emphasize at this point that it's not the only way to compute. In fact, it is definitely possible to do direct computations in this category and in this category. And these are what are basically known as natural operations in differential geometry. And it's definitely possible to write those down directly. In fact, there's a whole book about this called Natural Operations in Differential Geometry. So the reason I mentioned this construction is that it is useful for some examples, and it also directly connects to Lurie's setting. Let me write down maybe as a green arrow. Connecting to Lurie's setting, if we evaluate at a point, you land in simplicial sets with an action of OD. And that's precisely Lurie's setting. So in case you don't have any non-trivial smooth families, you just work over a trivial family indexed by a point. You will recover simplicial sets with an action of OD. And that's precisely Lurie's setup. Oh, and I should have finished here the recipe. To finish the recipe, the map in space can be computed as map in space in the other category from this bold S, which you only need to compute once, to well, W you convert it to also the same site by restricting. Okay, so I guess next time, if you are still interested, we'll do explicit examples where the recipes I discussed today will be applied to very specific examples. The first example will be a really simple, one-dimensional, oriented Riemannian field series. And in this case, we will recover precisely what you expect, which is a classification of one-dimensional oriented Riemannian field series as one-parameter groups of operators, exactly as you know them in quantum mechanics. So that's more or less the expected result. And I hope we'll also do some higher dimensional examples in dimension 2 and higher, which will perhaps illustrate the full power of GCH and the associated machinery. Okay, and I think that's it for today, and let's see if there are any questions left.
I hope I understand correctly that the last example is linked to ordinary quantum mechanics, yes?
Yeah, this is precisely just the traditional quantum mechanics, yes. Yeah, and there will be, of course, two-dimensional examples, which we hope to relate to a string theory. and conformal field theory and whatever. Yeah. Okay. More questions?
I guess it's a bit vague, maybe, but you said that it may be easier to compute in this category of functors from cart op.
Yeah, so you mean this one, right, on the right side? Yeah, so sometimes, like in this example, like we will do it, it's exactly how we are going to compute it, just for your benefit. But there are many other examples where it's, in fact, in many cases, it's quite easy to write down a morphism from S to W directly, because a morphism from S to W is nothing else than a natural operation in differential geometry. And we have tons and tons of such operations. In fact, I will also illustrate how to compute this directly. So maybe I should say this as a little remark. We can also be computed directly, and we'll do such complications. So it's not by no means like this last recipe is basically just one option, and there are many other options. So both direct complications and this recipe are also fine to use.
I see. Thank you.
Okay, more questions? And as usual, let me remind you that in our Discord server, you can communicate your ideas on what we should do next. In fact, I think I addressed maybe at least one or two of those requests today. I think Alex mentioned that he is interested in comparison to Lurie's setting, and that's more or less what we discussed today. And if there are any questions left, please mention them so we can add more detail. At some point, I will also, if there is still a desire left, I will sketch a proof. I think several people were interested in the proof, so if you are still interested, please let me know. Alex is interested, but maybe it's fine to say more than one time. This will help me prioritize what should be done first, and maybe what is more important and what is less important.
How many lectures are you going to?
Well, let's see. One moment. Let me think about this for a second. Just a second. Okay, so we'll meet on May 5th. Yeah, on May 12th and probably May 19th, I will most likely be traveling because I'm traveling in Germany the week of May 12th to 18th. So roughly speaking, plus or minus 1 or 2 days. So most likely I will not be able to meet on May 12th. I'm not sure about May 19th. We might be able to meet on May 19th. But definitely not meet on May 12th. So May 5th, we can still have a lecture. And after May 5th, we will decide. After May 5th, my plans should be settled. My travel plans, I mean. So May 5th, let me write down. So May 5th, we still have a lecture. Let's see.
Is there a conference in Germany?
Oh yeah, there is one in Greifswald. It's called From Analysis to Homotopy Theory. I'm pretty sure I must have forwarded to you at some point, but maybe I forgot. Yeah, so May 5th, there is a lecture. May 12th, probably no lecture. Almost certainly no lecture, but in fact, I might be able to lecture from Germany. So I will keep you updated. So maybe I should say possibly in our lecture, but not definitively. I will let you know later. And May 19th is kind of similar because, but probably we can have a lecture, but it's not totally certain. Probably we are going to have a lecture. Well, that's only if there's still demand from you guys. So it's well, 6 people survived to this point, so that's very impressive. But who knows how many will survive once we start diving into technical details. So let me maybe do a little opinion poll. I don't know, like if you guys can like respond in chat about what you are interested in. So the suggestions so far, the first one is maybe to look at more compute more examples.
Do you mean chat and Discord?
No, you can reply here right now. It's like an interactive poll. So if you guys are interested in computing more examples, the second one is maybe look at the proof of locality. The third one is a proof of the GCH part 2, the actual GCH. Yes. Let's see what other. The number 4 was maybe some. We can say something about tangential structures. I mean, it's not a particularly deep topic, or there's not that much to say. Maybe it's like 20 minutes, half an hour. I can explain everything there is to explain. Okay, and if somebody would also comment apart from Alex, because 2D CFT, yes, I will try to think something about 2D CFT, okay. 2D CFT is definitely an option. Anything else you guys want to see? Okay, examples, yes, definitely we'll do as many examples. Okay, 1, 3, 4, 2, okay, okay. Factorization homology, okay. Okay, anything else? BRST. Well, I will interpret BRST as an example of a gauge field theory, which we are going to write down. Yes. Anything else? Okay, so I think if it's, you can also mention it on Discord. Please feel free to leave, and please do leave comments on Discord, so we can see what else you guys are interested in. Like, it's fine to leave a vague comment. We can discuss, like, you don't have to be perfectly precise, or and I guess that's it for today, and I will see you guys next week on May 5th.
Thank you for the lecture.
Thank you. Bye.
Thank you.